Hello guys, welcome back to gas power cycles. We're gonna see the modifications to Bryton cycle. So it will be the Bryton cycle with intercooling, reheating, and regeneration. So if we recall what we did in our course in the analysis of Rankine cycle, we study or we explore the formula to get the efficiency, which is the network divided by Q in, and this network we can further explore it by saying that is the work of the turbine minus the work of the compressor divided by Q in. So if we want efficiency to go up, we can't make the turbine work to increase. We can try to reduce the amount of work that we are providing to the compressor, or we want to reduce the amount of heat that we are adding. So for each one of these we will have a strategy. For this we're gonna call it will be the reheat. For this will be the intercooling, and for this will be regeneration. We'll see that intercooling will reduce the amount of work, but at the same time will increase the amount of heat. So these two usually need to go hand by hand. So we're going to start with regeneration. And if we draw our TDS diagram for the cycle, if we draw a TS diagram for our cycle, if we draw a TS diagram of our cycle, we have our can see that the air that is leaving the turbine, which is at T4, it still have a high temperature, and so these gases we are just taking out to the atmosphere, and they are living with a high temperature with a lot of potential to perform work. At the same time, we are investing fuel to warm up from 2 to 3. So if we can preheat the air that's going to the combustor and have it to bring it to a closer temperature to T4, so this will be equal to T4. Let's say that we try to bring it to this X temperature. Because of that, the exhaust air will cool down to a Y temperature. Of course, this is not to scale, and here the effect is really exaggerated, but if we can do this, then we will save this amount of fuel, and we need just to provide this amount of heat. How do we do this? We can do this with a heat exchanger, more likely a counterflow heat exchanger. So if we have our air that is coming from the compressor and we are putting to a heat exchanger before we go to the combustor, and then we go to the turbine. This air, I'm going to change the color just to make sure that we differentiate. This air have high energy, so heat will go from this point to this point. In order to do that, we will need to have a delta T. So this will be our regenerator. We can close it to show that it's a closed heat exchanger, and just as a reference, this is our number 2 that comes from the compressor. This is the number 3 that comes from the combustor and goes to the turbine, and this is our number 4, the exit of our turbine. So if we plot it, let's say that we plot it along this line, this length, we'll have something like this. This is temperature, and this is our distance along the heat exchanger. So we'll have this vertical line too. This is still temperature. So I will have 2 streams. One will be the cold air, it goes from T2 to a known state that I call X, this MX. So this Tx, and I have the warm that comes from T4 to state T5. As we mentioned earlier, we need a delta T all the way to have heat transferring from the hot fluid to the warm fluid. Furthermore, we are gonna define this approach temperature. Okay, so we notice that we can gain some energy, increase the temperature up to Tx, and save that fuel. Okay, so for this heat exchanger, if we perform energy analysis, our first law will look like this. And I will include the summation of the masses, because at this point we only have one inlet and one outlet, but later on in the problems we're going to work with airflow ratio. We are going to include the mass of the fuel. So This is our first law for this open system. Now, this heat exchanger, we want to have it isolated from the ambient, so we will not have Q in or Q out, because we want all the heat transferred from the hot to the cold stream, not to or from the ambient. This is rigid, so we don't have any work in or out, and this is a steady state device, so this is 0. If we expand this, and at this point we are only having one stream, one inlet and one outlet, so we can drop the mass flow rate. We can see that all the streams that are going into the heat exchangers is H2 plus H4 equals Hx, which is this point, plus H5. So we notice that we have two unknowns, Hx and H5. So we need goodness. So we need some other information, and we're gonna use a figure of merit of how good this heat exchanger is, and we're gonna call that effectiveness. And use this figure of merit to an effectiveness that will tell us how well this heat exchanger is working for us. So in order to define this effectiveness, we're gonna say that this will be equal to the maximum heat that the actual heat that we are transferring dividing by the maximum heat that this could provide. If we make this heat exchanger large enough in infinite in area, or we allow an infinite amount of time to transfer heat, we can recognize that this delta T would approach to 0. And Tx will be equal to T4. Of course, this is impossible, but will be the maximum that we can get. So, if Qmax is equal to H4 minus H2, because as we mentioned, we make this temperature approach equal to 0, and Q actual is Hx minus H2, we can define the effectiveness as Hx minus H2, H4 minus H2, and with this we close our system, because now we have two equations with two unknowns. Please note that these numbers are arbitrary, that we usually have different numbers, and you should analyze each case and not go with this formula, because when we say intercooling, we will notice that we have a different number here. Okay, so this is how we analyze regenerative cycle. Now, for intercooling, me change the color so you know there's a difference. For intercooling, we discussed at Thermal 1 that cooling the air during the compression will reduce the amount of work, since it will approach a reversible compression. It will approach an isothermal compression. But sometimes it's not practical to do it. So what we can do is we can, instead of having this situation, where we having a big delta P, what we can do is separate this in two. So I will have I still have the same delta P, but now I have intermediate pressure, and in this intercooler we're gonna reject some heat. So if we assume that our compression work for polytropic something like this, and it's true for each compressor, we can divide this in two isentropic compressors with the same temperature in between, let's say. So we will have something like this. To pass from this relation to this relation, we invoke isentropic relations. Sorry, it's okay. So we can see that in these two, the only unknown is px. So we can use calculus you can find that the maximum to be when px or p1 equals p2 over px. That means that this intermediate pressure will be p2 over p1. I mean the square root of p2 times p1. So the effect of intercooling is shown here. What we are doing is we are compressing to an intermediate pressure, then we cool down, reducing its temperature. usually to the same temperature than the beginning, and then compress again. This is the intercooling portion that we are seeing. Usually this intercooling reduces the work of the compressor, but does not increase the efficiency, because as we can see here, we are adding the amount of heat that we need to provide. So we usually need to do it in parallel with regeneration. Okay. Finally, reheat. Let me change the color so we notice the difference. Similar to what we did in ranking, we may want to extract the gases at some point and add them and increase the temperature again. But we have a closed system. But the origin of reheat, it comes from metallurgical reasons. Tmax is a function of the material. So this material dictates the maximum temperature we can use in our cycle. So in order to protect, we usually inject excess air, that is more air than needed for the combustion. So that air helps to cool down the blades. Because of that, our combustion gases are still rich in oxygen. So we can use this O2 by injecting fuel again. So in this case, what we're going to do is we're going to have, let's say that we have our combustor, we have our turbine, and we're going to extract it at an intermediate pressure going into in a second combustor. This is the heater and this is the reheater, and then we pass it to a second turbine. Okay, similar to what we see in the intercooling, the optimum pressure, the optimum structure pressure will be when we have P. So let's say this is 3, 4, 5, and 6. So it will be, hold on, this is pressures. So we are gonna call this pressure X. Since we don't have any pressure drop, this is the same, and this is our original pressure form. So will be optimum when we have P3 over Px equal Px over P4, which again says that our optimum will be when we have this. So how does cycle with intercooling and reheat look like? Well, we have our intercooling section, we have our reheat section, and we have our regeneration section. So this will be the more general cycle that we are going to analyze. Watch next video for some solved problems with this cycle. Thank you.